Good afternoon, everyone. I'm Jon Harman. I'm from Ceres, and I'm the Technology Delivery Director. Today I'm going to give you an introduction to our company and also our solid oxide technology. So over the next 15 minutes, a brief intro to the company, what we're about, what we do, an overview of our technology, how it's used, in which applications, and our business model, which is quite unique in the space as well. Then I'm going to really zoom in on our SOEC, solid oxide electrolyzer technology, give you an impression of the progress we're making in that area, how we're planning to scale up, and some of the techno-economics associated with solid oxide electrolysis, and then briefly touch on our fuel cell applications as well, and where we're going with solid oxide fuel cell applications as well. So a bit about Ceres. So we are a leading developer of low-temperature solid oxide technologies. We're headquartered in the UK, but we have a technology licensing business model. So we license our cell and stack technology to global partners. They can use that technology, they can develop off the base technology, but they can also manufacture our technology in their factories, and we sell manufacturing licenses to them as well. So an overview of our technology. So we have a unique low-temperature solid oxide technology. It operates at a temperature between 500 and 600 C, and this is really enabled by an innovative Ceres-based electrolyte. And what's that do for us? Well, it allows us to print the cells onto a stainless steel substrate and interconnect. And that really uniquely positions Ceres' technology in a bit of a sweet spot. So you've got the same really high conversion efficiency from fuel to electricity, above 60% in fuel cell mode, and 85 to 90% LHV in electrolysis mode. And it's got the same fuel flexibility as higher temperature technologies as well. So it can run on, doesn't have to be pure hydrogen, it can run on natural gas, it can run on ammonia or methanol, for example. But there are three kind of distinct advantages offered by the low temperature of operation. So we're able to use low-cost, widely available materials. Secondly, it provides best-in-class durability and robustness because we're on a stainless steel substrate, so it's really tolerant to thermal cycles and emergency stops. It's real sort of real-world events, really. And it's also manufacturable at very high volume and quality. And this is really endorsed by the partnerships that we have with both Bosch and Doosan, who are building factories to produce our technology in Germany and in Korea. The other nice thing about it is it provides a really nice, flexible technology platform. So the same tech can be used both in fuel cell mode to generate very highly efficient electricity for distributed power generation applications. Again, I mentioned that fuel flexibility, so it can run on nat gas, blends of hydrogen, biogas, for example. But it can also be used in electrolysis mode and be integrated with industrial processes where heat is available, and you can drive some really, really high efficiencies in that regard. So we're looking at applications to decarbonize industry, such as green steel production, industrial chemicals, ammonia production, where it can be integrated with renewable energy or low carbon energy, electricity to generate best-in-class hydrogen production costs. So a few words on our licensing model. So here's some examples of where we've licensed our technology and inserted it into our partners' products, obviously in partnership with them. And this is all about generating those partnerships where we can have a mutually beneficial outcome. So I'm going to touch on the fuel cell products that our technology has been inserted into first. So our first licensing deal was with Miura in Japan. That came in 2016. And since that time, we've struck deals with Bosch, Doosan, and Weichai, who've been inserting our technology into their distributed grid reinforcement products, combined heat and power products. And now there's a lot of interest in generating shipboard marine power systems. So these started off at sort of 5 to 30 kilowatt blocks. But now Doosan are certainly looking at much bigger power systems in the 600 kilowatt range for marine applications. On the electrolysis front, we're a bit earlier in the maturation on the hydrogen front, so we're getting that technology out of the lab, and now we've built a first-of-a-kind megawatt class demonstrator, which you can see there, and we're partnered with Shell, Bosch, and Linde to deploy those demonstrators on their R&D campuses next year. So really getting it out of the lab and being able to show the technology operating at a really high efficiency in an industrial context. I touched on our manufacturing licensing business model. So we have 2 manufacturing licenses at the moment. Bosch in Germany are building a factory to make 200 megawatts of product a year. And Doosan in Korea are building a factory at 50 megawatts currently. They're both coming online next year. These powers are quoted in solid oxide fuel cell powers. In electrolysis mode, you can drive the cells at 3 times the current density. So actually, if these factories were used to make electrolyzer cells, you're looking at 750 megawatts of capacity from next year. We also have a reference plant based in the UK. This is a small capacity plant, but it demonstrates the start-to-end process of the manufacturing process at both rate and yield. So partners who are interested in taking a manufacturing license can actually see the products being manufactured and get a real feel for that, so they can be convinced that the manufacturing license is worth it. So some words on our megawatt class SOEC demo. So as I said before, we really needed to get the SOEC technology out of the lab and into the hands of end users. We're building 2 of these demo systems at the megawatt scale. This one here is on test in Germany before it's going to be transferred to Shell in Bangalore. You can see behind this system we've got a steam generation system that's delivering steam to the system at 150C, and behind that you've got AC to DC rectifiers, but everything else is packaged in that 40-foot container. The hydrogen that it produces will be then used by our partners at their demonstration sites. Inside that 40-foot container, we've got 9 of these prototype modules. So within there, you've got 8 of our standard stacks, heat exchangers, trim heaters, thermal insulation, and the DC power distribution systems. These are standard stacks. We've done no optimization for SOEC mode, but that's a program that we've got ongoing at the moment. So far, we've tested 7 of these modules so far, all with great results, ahead of system integration into that 40-foot container system that you saw earlier. The electrical power consumption is great. So at this system level, it's generating hydrogen at a consumption of 38 kilowatt hours per kilogram hydrogen. And in fact, these modules are being manufactured by one of our long-standing partners right here in the US. So with any new technology, the proof's in the pudding. We need to get these demos out at meaningful scales, and a megawatt is the starting point that we felt was a really good starting point. But it also needs to be demonstrated in an industrial context, but a non-commercial context initially. So we're planning 2 demos, as I mentioned before, one in Bangalore, one in Germany. These demos will run for 3 years in total. These systems are going to be fully instrumented, and we're going to hope to generate a really rich set of performance and durability data from these systems running in an industrial context. But we're not going to wait until those demonstrations are complete. There's a clear market pool for green and blue hydrogen, with most analysts predicting the size of the market in the range of 500 to 600 megatons per year by 2050. So there's a real opportunity for partners to license our technology and engage right across the value chain. So you can see here, we're laying out a very modular approach to the scale-up, right from cells through stacks to stack arrays, and then into deployable 4 megawatts SOEC modules, which can then be built in factories and deployed into 100 megawatt scale or gigawatt scale plants. And then really to touch on the anatomy of the levelized cost of hydrogen, really. So So we see SOEC as being a really great fit for industrial decarbonisation, where you've got some low-grade heat available, which may go to a cooling tower, but also you need always-on low-carbon power to drive those industrial processes. So in that case, you may be paying a little bit more for your electricity, your dollars per megawatt hour, because of those conditions. But the really high conversion efficiency of the technology allows you to really drive down the levelized cost of hydrogen. And you can see here that the electrical power component really dominates the anatomy of the LCOH. But we are really focusing on the CapEx element too. You can see it's a relatively small element to the overall component of the LCOH. But our low temperature technology really allows us to drive down the stack and stack array costs. And you can see that shown on the right-hand side, what we're predicting at high volume in terms of system costs for our electrolyzer systems. And then there was a great session earlier in the main auditorium about driving down project costs. And I think quite an interesting exercise is to look at how efficiency drives down project costs. So if you consider the effect of a significantly higher system efficiency of generating green hydrogen at an industrial scale. Now this case is generating 1 megaton of green hydrogen, but you can see, I suppose, rather obviously there's some significant energy cost savings because you're running at such a higher efficiency. But maybe what isn't quite so obvious until you look at it is you also drive down both the CapEx requirements and the capacity requirements for both renewables capacity and electrolyzer capacity and all the upstream electrical power supplies. So you get both a 26% reduction in the operational costs of the plant, but also a 26% reduction on the CapEx costs of the plant that's generating the same amount of hydrogen being produced. So life and robustness of our technology has a really strong focus at Ceres. And here we can see some test data. It's a technology talk, so I had to get some graphs in of some real test data. So on the left-hand side, we can see some long-duration steady-state degradation plots showing that a number of stacks all operating at less than 0.2% per 1,000 hours voltage degradation. That's in SOFC mode. And on the right side, this is really Ceres' party trick, best-in-class robustness for a solid oxide technology to real-world events. So no other solid oxide technology can withstand these sort of thermal cycles or emergency stops, which are things which are going to happen at plant level, at project level. And that's just an inherent robustness within our technology. We also see a really similar behavior in SOEC mode. I haven't got plots going out for 30 to 35,000 hours yet for SOEC mode, but we don't expect to see any particular differences in degradation behavior. And there is an opportunity in SOEC mode to further minimize degradation. You can do a little trick with gradually increasing the stack temperature to offset the effects of degradation through life in SOEC mode, which is quite interesting. So I've been focusing a lot on electrolysis. Just a few words on the fuel flexibility aspects for SOFC. So we have a future fuels program which is running at the moment. We're really trying to take advantage of the omnivorous nature of solid oxide technology. So we're testing the technology, and we're carrying out system design for operation on ammonia, on methanol, biogas, and also industrial grades of hydrogen. So just to sum up then, thanks very much for your attention this afternoon. So we've got three main technology delivery paths moving at pace at Ceres. We've got the stationary SOFC program for distributed power generation, grid reinforcement products, traditionally running on nat gas, but now looking to biogas and hydrogen blends, with also carbon capture technologies being looked at too. We're looking at operation of our SOFC technology on future fuels such as e-methanol, ammonia, and for marine applications. And also we've got the SOEC program for green hydrogen, which is a great fit for industrial decarbonisation. So the technology teams at Ceres, they're flying in close formation across all those three technology programs, really focusing on driving down cost, getting best-in-class performance out of the technology, and best-in-class durability. Thanks very much for your attention this afternoon.